Welcome everybody. Welcome to NEN, the Netherlands. And of course a very warm welcome to our ASTM colleagues who traveled to the Netherlands for their board meeting in Amsterdam. They have a very busy week, or very busy days. And it was a great opportunity to have a small conference here on a topic. And we were thinking what would be a good topic. First we thought, well, let's talk about cannabis. That was we discussed in December last year with Katie. We said, well, cannabis will be difficult because it's not allowed in the Netherlands and it's not legal. And we cannot make standards for that. So I was very impressed of the meeting, the ASTM group of more than almost 300 people. So we had to find another topic, and then we said, well, it's interesting what's happening in Europe, but also all over the world when it's about sustainable, energy efficient buildings. I think or even circular buildings, circular concrete, circular materials. So that was the ideal solution. So to have some exchange with each other on what's happening in Europe, what's happening in the Netherlands, have some good discussion around these topics, because we have the same vision, I think, from NEN, from ASTM and any other standardization body. We want to make standards which have impact on industry, on the community, on the industry, on everybody, on the entire society. And I also think that we should work together as standardization bodies, because no one is happy with having 40 different standards or almost the same standard, because it will not help with safety, it will not help for environmental issues, sustainability, it will not help all of us. My name is Harold Powell, so I'm the manager of the business unit standards, doing all the standardization business within the Netherlands, making sure our people who have an interest in standardization are served as good as possible, speaking of their voice in Europe in the global standardization business. Let's see if it's working. Yeah, before we go on, there is no drill today, but if there is an event, a big event, then we don't use the elevator, of course. We have the 2 stairs. You all already tried one. We go down the stairs and meet up in the place where, according to the standard, we have to meet. So we assemble outside of the parking, and we await instructions for from the people who are trained for that. So, but
when do we phone 111? First or after?
No. You don't have to phone it, but you can phone it. So those who you leave everything, don't take your stuff, don't take your telephone. You just yes. Okay. Let's see if it works. So something about NEN. As I said, what is the way we work together? Me myself, I was in energy for a long time, energy standardization, and we had a lot of cooperation with ASTM because the fuel market and the oil and gas market is a global market. It's a little bit different with the construction sector. And with the same thing that I just mentioned before, it's very important that we have the same goal. So both NEN and ASTM are standardization organizations. We have the same thoughts about quality, the same thoughts about adoption. And we have also a lot of members, also in the Netherlands, and of course NEN also with its global environment with SAM and with ISO. I think that's also the difference. I will not go too deep into that. ASTM is really a member organization, and is of course also a member organization, but because organizations are member of our committees and countries are part in SEN and ISO. That's the main difference between ASTM and NEN. And circular construction, well, we have the same momentum, the same needs. Maybe one country is a little bit further and other countries a little bit behind, depending on which topic. But these are the questions. The questions we discussed today will be the questions of the next 5 to 10 or 20 years. Something about NEN. So we're almost a little bit younger than ASTM, but we're about 100 years, more than 100 years old, I would say. You see two establishments. One is on our electro and ICT side. We have two ones, and 1916 was NEN as itself. So we're the second one in Europe. 290 employees. We're part of well, we're the national member of CEN and ISO. We have 5,000 active committee members, and of course behind them are a lot of companies. I always say behind them is the entire Netherlands, because that's members of hundreds of thousands of companies and stakeholders in the Netherlands. We have four focus areas, and that's and these are the big challenges for every one of us, also for you, for our government, for our industry, for our NGOs, etc. So smart industry, everything what's happening with the digital transformation for industry, for companies, for society. Circular, as we discussed today. We have a lot of projects now on related to the circular economy, not only in the building sector, but also with clothes, with the plastics, for instance, just some to mention. Energy transition, of course, with the discussions on energy and also the transition we have to make, at least in the Netherlands and in Europe, we have a very big discussion on that. I think that's a global discussion. A lot of new standards will be needed, so that's why we focus on that. And water, we just mentioned downstairs to each other, well, there are two big challenges. It's energy. For welfare, you need energy and you need water. Netherlands, it's not a real big discussion maybe, but we say, well, water is a problem of the next 20 years. So we will have to make sure that the standards are in place, which we need for good water supply, good water quality, etc. What we do, not only standardization, we also do scheme management. So we develop certification schemes in line with the standards development. We don't certify ourselves in the Netherlands. And then some other figures of, so our business model is we get profits from selling standards, and we get fees from the companies who have an interest. So these are the figures on our sales from. We also sell ASTM standards because our customers like a one entrance. So we have them in our portfolio. If you go to NEN Connect, and there are some information over there. They can be in your NEN account, so that's a NEN Connect account. Our mission, I already mentioned it a little bit, our core values. So what we do is we connect people, we connect stakeholders which have an interest in a certain topic, and all with the aim to improve safety, the economics, safety, durability, sustainability, and in the buildings, of course, construction sector, you can imagine that's an important one. The construction sector is both nationally as internationally oriented, and it's a big theme within our company. And this is what I already mentioned, particularly this one I want to mention. So in the building side, we are working together with a lot of stakeholders on, as we call it, the platform circular buildings 2023, with the aim to have those standards in place for a circular, at least circular construction sector. And my colleague is over there. See if you want to know more about that platform, then you can ask Boukje. And it's interesting for me to see what's happening over there. So that's about NEN. Any questions on that to me at this moment? Otherwise we skip to my colleague, my counterpart within, not my counterpart, sorry, but to the introduction of ASTM. Let's see if it works. Yes.
If it doesn't, I'm going to do shadow puppets.
Yeah. I jump in if it's needed. Please introduce yourself.
Okay, I will. Thank you. Thanks, Harold. I'm going to take. Is it moving? I want to thank NEN and Harold for having us here as a partner. NEN's been a particularly good partner for ASTM, not only in selling our standards, but in collaborating with us on development of new standards. And it's great that we're here, and it's fortuitous that we're here in the Netherlands to be able to talk to you today, because there's really never been a more important time or more interesting time to talk about standards development. The four pillars, or the four strategic themes that Harold talked about, really changes the way standards and product development and product integration is being discussed. 100 years ago, when NEN started, ASTM started about that same time. It was really about, how do I know this product, the wall's this thick, or what is it made from? Now it's changing to, what is the performance of the material, the product, and in the end system? And then how do we regain that back and not lose the value of that product as waste? And that's really what the circular economy, circular construction is all about. And so it's great for us to be here to talk to you about that. My name is Andy Coretta. I actually have two jobs. One I get paid for, and the one I'm doing today is free. In my day job, I'm Vice President for Copper Development Association. It's a North American trade association for the copper producing industries. We are closely aligned with the European Copper Institute out of Brussels, Deutsches Kupfer Institute out of Germany, the International Copper Association that brings all of us together and really works on development of research and development, education, market development for the entire copper industry. The job that I'm here for today, I am also Vice Chairman of the Board of ASTM International. And just to give you an idea, the board of ASTM International is an entire volunteer board made up of 24 select volunteers that come from a variety of technical committees. And so we're here this week discussing ASTM's future strategy, new development areas. As Harold mentioned, 2 years ago we started a committee on cannabis. We've started new committees on drones, unmanned spaceflight, human spaceflight, exoskeleton. So all new technology areas we've started new standardization work on. And that's what the board really does. We're here to talk about where ASTM is going in the future, how we work with our partners, and that's what we're here for this week. We've enjoyed your great country. I've especially enjoyed walking around Amsterdam. There's things that we wouldn't normally see in a U.S. city, and it's been a lot of fun, so thank you. Just a few of the numbers around ASTM. Just a little bit older, 120 years. Right? So we're in the same range. Survived through the standardization business for quite a long time. We have about 33,000 volunteer members that work to develop these standards year-round. They cover all sectors of industry, business, academia, general users that come in really looking for how these standards are going to help them in their businesses, consultants, consumers. We have about 150 technical committees that cover everything from mine, which is copper, we said cannabis. We've got a number of people here representing concrete that will speak to you today, building performance, 150 committees. Under those, we have about 2,000 subcommittees, and we have right about 13,000 ASTM International consensus standards out there in the marketplace. We are truly an international organization. We didn't just tag it on the end of ASTM. We have quite a few volunteers in all of our technical committees from around the world. We're committed to the World Trade Organization principles of standards development, transparency, openness. ASTM standards have been cited 8,000 different times outside of the US, and nearly half of the standard sales that come into ASTM are outside of the United States borders. So ASTM standards are truly used internationally. We have 6 offices, including one in Brussels, our European office, and we have 110 memorandums of understanding with countries around the world on the use of ASTM standards. So truly a global reach, most of which is facilitated and helped greatly by our partners such as NEN. So for my paid job, I managed to sneak a few slides in here. So I do work in copper, brass, and bronze, the copper alloys. One of the first real engineering materials used by man. and is actually the most highly recycled engineering material. And by that I mean aluminum is probably the most highly recycled material, but you're looking at aluminum in beverage cans and things like that. You're not using it in an engineering purpose. We estimate about 2/3 of all of the copper that's been produced in the world, so mined and made into a product since 1900, is still in use today. Probably not as the same product, but it's been brought back in a circular manner and recycled. About 35% of all of the copper in any copper product produced today is a post-consumer recycled content. 9 million tons of copper recycled annually globally. The benefit of doing this is when we take copper, and it's one of the few engineering materials that we can take, recycle exactly back to its existing form. We don't have to downcycle it. And so we can take it right back to the existing alloy. That saves 85% of the initial energy put into the product. So it's really, copper's been living in a circular economy manner since its inception. This allows us to actually give a savings of about 40 million tons of carbon dioxide annually. That's like taking 16 million internal combustion engine vehicles off the road every year. Okay. Why is this important in construction? This is an eye chart, so I don't expect you to read it. What this is this is a stocks and flows diagram of copper globally. So new copper coming in up here, the width of the arrows, of the lines shows you, is representative of the volume. Works its way from production down through, and then it hits this big box right here that's really not to scale. And that's copper in use. So that's the wiring in this building. That's the plumbing in this building. That's the copper sheet on the architectural sheet on the exterior of the Nemo Museum in Amsterdam. That's in use, and it's going to be in use for quite a while. Right, so it builds up as a material bank, and so it tends to be forgotten. You know, we think of recycling for things that are single-use plastic, where we see in the oceans it's building up. This is sitting out there as a future material bank that we can use, but we have to think about it now, right? And 47% of all of that copper that's out there, copper, brass, and bronze products, is in a building, right? So we really need to start thinking about how do we deal with this for the end of life and bring it back. And so that's why this is particularly important to us. Just to give you an example, you know, most copper products, we expect them to last beyond the life of the building, for 50 to 75 years. They're not often replaced. We don't think about it. And this is an excellent, I put this here because I think this is an excellent example. This is the Parliamentary Library in Ottawa, Canada. And they were having issues with the roof. This copper was on this roof for over 100 years. The underlying roof structure had problems. They had to fix the structure, so they removed all the copper off of the roof. And they didn't want to scrap it. They didn't want to recycle it, send it back to the scrap stream. So what they did is they took that copper and they used it as decorative elemental ornaments architecturally throughout the building. And that's the Parliamentary Library. So it's truly a reuse, not a recycle. We don't see that all that often, but it's things that we need to think about if we truly want to reach a circular construction economy. As far as what the copper committees are doing, we're thinking about it all the time. Now what we're working to do is improve the long-term recyclability of copper. Most copper that's used out there is not pure copper. There's, in the US, in North America, in our scheme, there's over 800 copper alloys. So we took copper and we add tin to it, or we add zinc to it, or we add bismuth to it, or whatever it might be. Well, when we do that hinders the recycling downstream. So we have to start thinking about how do we deal with that. So we're doing that within the committee. We're actually looking at technology to improve the recycling practices to help us do that. And then we're doing such things as looking at most electrical copper out there, copper wiring, is 100% pure copper that just came out of a mine, cathode copper. But we're working on technology to use a new technology, fire-refined high-conductivity copper that can take scrap, turn it into electrically pure copper immediately, so that we can regain all that, because 55% of the use goes into electrical products. So it's an example, copper's an example of really how we need to think about this circular construction economy, and that we need to think long term. One of my dreams would be if we put the wiring and the piping on the outside of the wall, it'd be much easier to do, but architects aren't going to do that, right? So that's all I have. I have to introduce our speakers, so I'm going to go back up here quickly. So we have a number of speakers here today. I'm not introducing them in any particular order because we have 2 sessions. So we have Chris Mathis with us. He is going to be a great panelist in terms of addressing energy efficiency, durability, sustainability, and other aspects of building performance. He's the president of Mathis Consulting Company, a firm that provides professional services in the building energy efficiency and sustainability space. He's active on ASTM committees, including sustainability, which is E60, and the performance of buildings. And I know from speaking to Chris this morning, you're going to hear the word performance throughout his presentation. E6. They're particularly well known for their large footprint across material durability, energy efficiency, air leakage, overall performance of a building. Chris has published books and technical papers, regularly conducts training programs for builders, architects, engineers, building officials, utilities, and policymakers on a variety of building science topics. He earned a master's in architecture studies from MIT and a bachelor's in physics from the University of North Carolina, Asheville. So Chris is sitting here on this side. Welcome, Chris. Cesar Constantino, sitting at the other side, is the Director of Business Development for Separation Technologies, which is a Titan America business. Separation Technologies is a leading producer of processed fly ash in the United States. Cesar is active in well-known ASTM committees such as cement, which is C1, as well as concrete and concrete aggregates, C9, and sustainability, E60. Cesar was a researcher and a consultant, both in Panama and the United States. In 2005, he joined Titan America's Florida business as a manager of technical services, rose to Director of Concrete Technology, then Director of Process Quality, and Vice President of Corporate Engineering. Constantino holds a bachelor's in civil engineering, a master's in structural engineering, and a doctorate in construction materials from the University of Texas. And he's going to share some thoughts with us today on recycling of concrete and other issues with fly ash and concrete. And then finally, for our morning session, our other speaker right in the middle, Oliver Delery. He's a vice president in technical marketing for North America for a company called Forterra Building Products, an international building products company that manufactures concrete pipe and construction products. Oliver is a past chairman of the Committee on Concrete Pipe, C13. And Oliver and others here know that concrete pipe uses industrial byproducts, such as those that Cesar is going to talk about, fly ash and slag cement. And I know that a focus in their industry is toward ensuring long-term economical life as well as recyclability of their products. Before beginning his career with Forterra, Oliver held positions as Gulf Coast Vice President and Corporate Engineer at Choctaw Incorporated and as President of New Orleans Cement Products Company. He holds a bachelor's degree in civil engineering from Tulane, and he's a licensed civil engineer in the U.S. states of Louisiana, Mississippi, and Texas. You want me to introduce the afternoon one or wait till later? Would you want me to? It's up to you. We can wait and do this when the afternoon session comes or for the second session. Which one? I'll do it.
Yeah, you do it?
Yeah.
Let's continue.
Okay. And Jack, would you stand up? Where's Jack?
I'm over here.
You messed up the seating. All the ASTM folks are over there. All the NEN folks are over here.
Integrated with your
Okay, we appreciate that. So Jack will be speaking in the second session. He's a research professor at Tufts University School of Engineering in Massachusetts. He chairs ASTM's Committee on Soil and Rock, D18. Before joining Tufts in 2015, Jack held several teaching and research positions at MIT. He focuses on geotechnical and geoenvironmental engineering and investigating geomaterial properties in addition to his teaching responsibilities. So Jack's pretty busy. He holds a doctorate and a master's in geotechnical engineering from MIT and a bachelor's in civil engineering from Worcester Polytechnic Institute. And among other things, Jack's Committee on Soil and Rock They develop standards and test methods in areas such as organophilic clay, which helps remediate contamination in sediment, soil, and groundwater. So these are the ASTM presenters who will be here today, and I thank you for giving me time to introduce them to you.
So, let's probably curious about the program. So the program is with 2 sessions, a little bit ahead of schedule, but no problem. We will catch back to that. First session is with, both are on circular design and construction. So the idea is just to listen to the 3 speeches or presentations, and then afterwards we'll have a discussion with you guys. So, and of course, you may be critical, ask strong questions to each other. After the coffee break, we will have 3 Dutch people and 1 STM people, and we will continue from a little bit different point of view, also on circular design. So, and after that, we will finish with some closing remarks from my side, and I think also from the STM side. We can say that. Yes. So, who may I give the floor?
Take it away. No problem.
Let's see.
So we're starting with
That's yours. Let's
Constantino,
see.
the last one, yes.
Yeah. Just click it.
Yes.
Yeah, oh, this one.
Perfect. And for pointer, in case
Yes.
yes, this will work. Okay. Excellent.
I will keep the time.
All right, so Cesar Constantino, thank you for joining us today. I am more than honored to participate in this activity, and I will admit that in casual conversation throughout this day, I'm truly inspired about the thinking that's happening in this room when we have the opportunity to talk to a developer, and I hear the theme of the circular economy and how what used to be for me, start with the end in mind, it's already history. He's starting with what the future is in mind, because the end is the beginning of what's next. And these are the kinds of things that make us resonate with the type of presentation that we're giving today. The other element I wanted to talk about is cement and concrete. But I cannot do that without putting the cement and concrete industries and the cement and concrete into context. And so that's why I start with a little picture here with some kids, and I highlight that by the time that these kids are 50, they will have likely produced 12 children, okay? Yes, maybe not in Amsterdam, but somewhere else, okay? And in turn, they will have had 30 more, by the time these kids are 50. But that means 62,000 hours shopping. And they're gonna be shopping in concrete malls, okay? They're gonna be also living in different residences. They'll move around, and they will have 35 residences that have relied in probably 3,000 tons of concrete walls, foundations, and sidewalks, etc. And they would have driven across 165 million cubic meters of concrete roads and highways. And then look at the number there in terms of water. And I knew we were going to have some concrete pipe experts in the panel, so this is about how much water is going to have to go through concrete pipes and concrete containments. So concrete matters. The numbers are huge. Therefore, smart use of this material is essential, and it is very important. And again, we connect basically concrete to expanding world economy. And the way that happens is we rely on concrete in our built environment because, plain and simple, it makes our living easy. It takes us places. So concrete is an active player in society. It connects society. It gives us safety, and that's the first place we go when we call home is, we rely on concrete. And certainly, as part of the economy, provides a local jobs in the various locations that we live in and work. But this is the built environment, and then this all permeates and goes into ASTM International, where we do standards and we provide additional services surrounding what the standards participate in. I am a member of Committee C1 on cement, and this committee has been active since 1902. And this is not a complete list of subcommittees, but you can see hydraulic cements, masonry cements, et cetera, et cetera. This is the list of subcommittees in areas of specific technical expertise where different standards are developed. And very importantly, the standards become updated periodically. So a lot of the activities is not just to develop a new standard, but those that exist to keep updating themselves. And then in the concrete and concrete aggregates, this is 1914. I am missing a number here. That's because I stayed too late last night in the rooftop of the W, and so I'm sorry, but 1914 goes there. And then, again, a partial list of the various subcommittees in the cement, the concrete aggregates committee. You will see aggregates, chemical admixtures, ground slag, petrography, and so forth. So in terms of technical documents and standards, you will see ASTM involvement throughout the world in these areas. And another area that I saw in NEN, when you talk about an operator of some other, or schemes, ASTM is also present in that space. I tried to find more letters to make this title more readable, but I couldn't. So ASTM plays a role in what the product category rules entail regarding the life cycle analysis of various products, and then the environmental product declarations that go along with it. This matters because once you have the products, all of a sudden you have to be able to measure things, and then you need to be able to make a determination of what makes more sense, what's more suitable for a certain location. And these are areas that ASTM is active. This is an example, an illustration of a product category rule for construction aggregates that is housed and developed. If you go to the ASTM International website, you can actually download and obtain the rules, and you can actually see a number of EPDs that have already been generated, again, in the construction sector. The bullets here simply identify the sections or the areas of environmental burdens that get estimated for each of the products evaluated. And for illustration purposes, you will see here, this is one of the EPDs where ASTM International is shown as a program operator. And this is actually being used by Eminet's Beton Ready Mix. So here's an example of the international scope of ASTM. This is not just about the United States. This is right in the Middle East, where you have an EPD and the presence of ASTM International. One of the items that I think is very important, as we see a product, we see a material, and we see it going for use, maybe an engineer determines this is the mix I want to use for this particular application, is that going forward and thinking not only with the end in mind but the new beginning, is that ASTM now, it's basically connecting a series of what used to be individual dots. Now ASTM is connecting those dots in that it doesn't start with the product or how it's used or who's going to use it. It starts with even development. So from the R&D territory, ASTM is present. I have been an industry liaison with the MIT Concrete Sustainability Hub in the United States, and it just so happens that we are using standards that are in the market from ASTM International at a macro scale, and all of a sudden implementing those ideas as to what led to the standard creation, and we're using them at the nanoscale. So for example, nanotechnology in the concrete sector in the United States is already at the research end with an intent of something else, but again, the circular thinking here is that what works at the macro scale can be influential and valid for us to consider in the nanoscale. So again, ASTM goes from research and technology, standards are created, then it goes into the market, but then this in turn continues to loop in further development. Again, ASTM International turning gray to green, and this is not just concrete being green by pigment. The idea here is to say we want to make it truly green. We want concrete to be low environmental burden. And some of the things that I will highlight in terms of more precise specific standards is when you look at the standard specification for concrete aggregates, for example, this number here means it's updated to 2018. So every standard is going to carry this designation. It tells you when is the last update. And we are required as technical committees to keep updating them after so many years. This standard will provide already, so this is has been done already for many years, the use of crushed concrete as aggregate in ready-mix concrete. And of course, there's some requirements, and the standard will go into the details of what compliance is needed in order for this application to happen. When you look at blended cements, you will find that, for example, limestone addition, which is a very common occurrence in many areas in the European Union, addition of limestone cements, that's something that actually made it into the standards in North America as a blended cement with the intent of lowering the clinker intensity per ton of material. And so performance matters, at the same time environmental footprint matters. So this has been already incorporated in the standard here. And the performance specification for hydraulic cement is also available, where as long as you provide the user a list of what's in it, as long as the performance is there, you're okay to use it. On the ready-mix side, and I'm going to spend maybe a little bit more time on the ready-mix side, is because of scale. I'm talking about a lot of concrete going to the United States. If you look at the possibility of positively impacting 6 to 9 million cubic meters of concrete, or 190 to 750 liters per truck, what the United States is trying to do, with influence from National Ready Mix Concrete Association and all of our members from South America, etc. You heard us that there's members from all over the world in ASTM standards, is to address the return fresh concrete. Okay? There may be a truck that goes to a job site and then there's 2 cubic meters left over in the drum. And today, without a standard, everybody is doing a different type of concept in terms of what do they do. They make blocks and then they sell them, or they crush it and use it as aggregate. But the thinking of, if you do that, you already wasted energy. The idea is, if you leave it in the drum, what can you do that you can batch new concrete on top of the existing concrete and provide a product that performs to the user, to the customer? And so basically this standard that started in 2016 actually provides, what are the things that you have to measure and what are the requirements that you need to follow. For example, if it's more than 90 minutes since the original batch of concrete occurred, okay, you're going to have to use some specialty admixtures in order to control hydration. And by the way, you got to measure the temperature. That concrete cannot be more than, let's say, 38 degrees. I converted from Fahrenheit, so that's why you see the decimal. But the idea is you now have a standard test method and a standard procedure here that actually helps the ready-mix industry. Whoever is using the standard, again, it could be in Panama, I'm from Panama, you could use the standard because they follow the ASTM international standards in order to do this. But I like the slide I think I saw from you where you said that you're looking for a passport of materials. And this is important because now in concrete, many people like to use fly ash as a way of supplementary cementitious materials, lowering the clinker intensity, therefore lowering the environmental burden of concrete. This is in the United States. The production and use of fly ash because of pulverized coal power generation. If you look at the last 10 years, there's been a significant decrease in terms of fly ash generation. That means less coal being burned. Yes, good, except if you're a ready-mix concrete producer that wants fly ash. The interesting aspect is that the industry is holding strong in terms of utilizing this percentage, means 60% of the fly ash generated in the United States is currently being used. And the issue here is that with less generation, what do we do about it? Okay, so this standard does not exist today, but it's a work item. This means there's technical experts in the ASTM body of experts working. This is a work item, no year because there's no standard yet, and it's titled Harvesting Coal Combustion Products Stored, see another W at night, too much drinking, in active and inactive storage areas for beneficial use. Okay? And basically what this says is it provides guidance to go into a landfill. This is a picture of a landfill. And you can take the cap off. This is a clay cap to prevent from water going through and then having heavy metals or any leachate to go further. But you can then now have access to all this. Why? Because for those engineers in the room, somebody already did this. They took the area under the curve, right? So if this ash was generated, this was used, all of this is buried in the ground. And this adds up to what about 1.5 billion tons of fly ash that exist in the United States, which means that we can now start mining fly ash, even if they're not burning into the power plants, okay? And so this, of course, you may need some beneficiation technologies. That's when you hear separation technologies where I work, that's what we do. We take the unburned coal and separate it from mineral. But the idea is now this could be the future of where we're going to find fly ash that doesn't exist. And I know in the European Union, of course, there's many areas that are losing the ability to have fly ash. See, every white dot here means in 2017, we already know that there's a coal power plant closing. So there's a lot of closures happening in Europe. Somebody's going to need fly ash, so we need a passport. We need fly ash to travel. We expect that over the course of the years, you know, this is the forecast. Look at the slope of this curve. The forecast is there's going to be a lot more seaborne trade of fly ash, but specifications need to be able to allow us to work together. The Australian fly ash does not meet the same spec as the European, nor the same as the ASTM International. No. So there has to be some work. So in closing, because I know the time is precious, we are connecting dots, as I said earlier. ASTM International is all about connecting the dots from research and development to a market and to utilization. And of course, in the construction industry, cement and concrete are after lowering environmental footprint. ASTM standards are tools that enable us to do that. So that plays directly into the sustainability and resilience of the built environment, but it's key to collaborate, to harmonize standards so that they can actually, with a passport, travel. So we want to help the work better. Thank you very much.
Let's continue. So we do the questions during the seminar, during the discussion. Let's see if it works. And then we have, let's see, Oliver, yes, Oliver. This should work. Try to stick to the time.
I'm Oliver Delery. You might not recognize the name Forterra. For 10 years prior to that, we were part of the Hanson or Heidelberg Cement Group. And then we were sold to a private investment company in the United States, and we changed our name to Forterra. I'm from New Orleans, as you know, and we've learned a lot over the years from the Netherlands. We're a city below sea level, just like Amsterdam. Unfortunately, one thing we did not learn before Katrina is how to keep the sea out of the city. You know, all of our rainwater and all, we have canals and we pump it all out. But when we had the surge from Katrina, all of the seawater came in over those levees and came into New Orleans. So now we've learned, we've built a brand new barrier out there, and a lot of our engineers had come over to the Netherlands after that, and thank you very much for the help. But unfortunately in the United States, we try to do stuff, you know, on our own. Like we're the ones that invented McDonald's and Burger King and all the trash that comes with that. A lot of low cost, unfortunately not recyclable materials. So we're going back now and trying to learn to recycle, trying to make sure we're building resilient, sustainable construction. What does resilient construction mean to us? Well, in the United States, just in the first 9 months of 2017, we had 15 weather events that cost over $1 billion of damage. And you need to be able to prevent that in the future and not have those same events happen again. If they're going to happen, you have to make sure that the cost is lower because you have built up resilient facilities. These weather-related disasters included everything from hurricanes to tornadoes, electrical storms, droughts, fires, freezes, flooding, and hailstorms. We have a lot going on this year in the United States, and many of these will result in damage or destruction to our infrastructure systems. And the last thing you need is to have infrastructure gone either right before a natural disaster or right after a natural disaster. These are where the disasters happen, so it's not just in certain areas of the country. You know, we have hurricanes across the Gulf South and where we live in New Orleans, but the forest fires in California, in Colorado, droughts, river flooding in the Midwest. So we have to define what resilient systems are that we need to design to. And resilient systems are those that can absorb a disturbance but still retain their basic function. In other words, for evacuation routes, you want something that you know is you're going to have problems with that, but you want piping systems, I mean the concrete pipe, that will stay there after the storm. Because it's very, very important to be able to get people out before a storm, but then have the emergency responders come back in after a storm immediately to start assessing the damage, look for people who did not evacuate. And that's critical right now. You're seeing it going on after Hurricane Michael in Florida. They're still trying to get back into some areas because we had built systems, roadway systems, evacuation systems, that were not resilient, that were not dependable, where the roadways all got washed away. So we need to upgrade that. Sustainability is frequently defined by its association with recycling and reuse of materials. So we're starting to bring that into our construction and in our manufacturing processes. Sustainability of infrastructure relates to the efficiency which those resources are used. Basically, structures that will not only last today and tomorrow, but will still be here 100 years from now. And if we look at a lot of the European cities, a lot of your infrastructure has been in for hundreds of years. And that's something we're learning in the United States, that you cannot build infrastructure systems for 50 years. Our interstate system was built about 65, 70 years ago in the United States. Now we're having to replace parts of that. And those are major evacuation routes. We needed to build those systems up to where they last 100 to 150 years, and all of the infrastructure below that, so the only thing that you're changing is the pavements themselves. The durability of a subsurface system directly relates to its sustainability. So we've got to have systems that are sustainable, and what are those keys to sustainable, resilient subsurface infrastructure? It's got to have a long service life, resource efficiency, durability, large event capacity, continuous or briefly interrupted usability despite the disturbances. In other words, if you have a drainage system where the road gets washed out, if your system is still there, you can very easily come back in, cover over it, and bring people in a day. Whereas if the entire drainage system or bridges got washed out with that, then you're looking at weeks and months to bring people back in. So we're trying to elevate our standards so that you have these resilient systems, and we know that nothing is completely disaster-proof, that there are going to be some problems, but you need to be able to be resilient to those problems. So major disaster resistance has to include those high volume duration rainfalls, the flooding, wildfires, landslides, sinkholes, earthquakes, tornadoes, and terrorism now. Oh, hit the wrong button here. There we go. You can't have this coming in. Now that was another piping system that after an event, the pipe collapsed. And these are the emergency responders getting back in. It's going to take them a day just to get the truck out, much less be able to repair that system and get something else back in. That just can't happen anymore. City of New Orleans, our drainage system after Katrina. 80% of the city was flooded. And I don't know if you know all the events. Part of it was flooded because of the seawater that came in, but part of it was because of an engineering design. We have, as I said before, we collect all of our rainwater. And all the rainwater goes into the local systems and then into canals, east-west canals feeding north-south canals to take it to pumping stations to pump into the lake. Well, on those canals going out to the lake, in building the sheet pile walls for the drainage canals, they misread the sand layer. So when they were putting in the sheet pile walls, they went to 17 feet, which was a very 6-inch layer of sand rather than 36 feet. Well, the bottom of the canals were 18 feet deep, and the storm surge that came in was an additional 12 feet, so you had 30 foot of head on a sheet pile wall. In 3 different cases, the exact same problem, because they tried to skip on things. They tried to go in the cheap. And because of that, 80% of the city flooded. Now, major street damage and subsidence, because the water stayed there for 3 weeks. So you have the streets coming up and down and all. Luckily, we got some money from the Federal Emergency Management Agency. It's a national firm that will come in and help cities redevelop. But our drainage system was 100% concrete pipe. My grandfather started our company in 1932. We have had no structural failures since 1932 of any of the pipe. Now we have had, because of Katrina and the streets, some of those pipe joints need to be repaired, but no collapses of the pipe. So we've been able to, it's been 13 years now, and we've been able to continue to live on that system while we're bringing back the streets one at a time. So we didn't have to completely shut down the city, put a whole new drainage system in, a whole new sewage system. We can do it now at our pace when we have the money to do it. So there were no structural pipes failures allowing, as I said before, that system to continue. So the significance of concrete pipe properties. We need to have, in this resilient infrastructure, you have to have the compressive strength. You have to have the density, the absorption, water cement ratios. All of these are important. After the New Orleans event, we started talking to our Congress and said, this is so critical. In New Orleans, we had to evacuate 2 days before the storm over 1 million people that had to leave the city. We needed to get those emergency response people back in. And we couldn't have done that unless we had a very good infrastructure system. But there are other places in the country that have grown very rapidly that don't have that type of infrastructure. And we're finding that in California, we're finding that in Colorado, where the forest fires will come in and pipe will melt or burn, and roadways have collapsed, and you're cutting off people. Either they can't get out or they can't get back in. So what we've talked to Congress about, and the president just signed a bill about 2 weeks ago, it's the Disaster Relief and Recovery Act, where they've finally gotten to a point where they said, yes, we will pay more up front to bring in more resilient, more durable, more sustainable systems, even if they cost more. We'd rather have that going in at the front, so when a disaster comes back in, we won't have to repay every time for the same system to go back in. You know, and that's what they were doing before. If you had a cheap system, that's all they would put back in as a cheap system. So now they're looking at foresight and saying, no, we have to increase these systems up front. Our committee C13 on concrete pipe, this is just some of the standards that we have. We control over 180 standards of concrete pipe, precast concrete products. All of our standards include material standards. And in those material standards, we're using industrial byproducts by including slag cement, natural pozzolans and coal fly ash, and silica fume. And that helps with the workability of the product, helps with the cohesiveness, the finish, the durability, to give us that 150-year lifespan. And as I said before, most of those pipe, when you put them in the ground, you're going to change the pavement on top of them. You don't want to change the pipe for a long period of time. No one has the maintenance money to do that. So in all of the design standards that we have for design of concrete pipe, we include Portland blast furnace slag cement. We include slag and fly ash, so that we're reusing these products, one, to make ours better, but also to keep the energy costs down of making the products. So we're also looking at research into the future. We're looking and have just completed standards on the use of synthetic fiber reinforced concrete to take the steel out of the pipe and use fibers. And in doing so, we're able to take the wall thicknesses and cut them down. So we're using less concrete, more fibers. It's becoming almost like a flexible pipe, but it's actually saving us a ton of energy. And we're also looking at the same thing with steel fiber reinforced pipe, where you're taking out your steel cages and adding smaller steel fibers for your tensile strength. In doing so, we also need members. Now, our committees are set up differently than NEN in that as a producer of the product, we can only have 49% membership on a committee. The other 51% has to be from the users, the end users, either the state highway departments, city engineers, consulting engineers. So we're constantly looking to get them involved in the committee because these are voluntary standards. And we want to make sure they're consensus standards so that they're accepted across the world. So we're constantly looking for new members. If any of y'all would like to join our committees, we'd love for you to. Our committee on concrete pipe just finished our meetings in September. We met in Cleveland, Ohio, and next September we're going to go to Victoria, British Columbia to meet. However, the committee meetings for ASTM are ongoing. This month we have committee meetings coming up in Washington, D.C. in October, November, and December, and each one of these committee weeks has approximately 30 different committees that get together at the same time to save money and travel and to continue developing these standards. So again, we'd love for anybody to join ASTM. It's $75 a year, so it's a bargain. But in the concrete pipe side, we're looking again, being from New Orleans, we're learning our lesson. You know, we have to look for the future, to make sure our children aren't having to repay and redo their infrastructure for us. Thank you.
So it's a completely different view. I think we go to another view here. To Christopher. It should work. Yep, go up and down.
Thank you. Well, Cesar and Oliver stole most of my messaging, so no. We actually didn't coordinate our messages, but it's interesting how we're saying many of the same things. I titled my presentation "Toward a Truly Sustainable Built Environment" because I think that that's something that's difficult to define, and I'm going to specifically talk about prioritizing building performance. I was here in Delft last week, and I noticed that, you know, here in the Netherlands you have lots of history of standards. This building, which was where the trade and the weights and measures were done, was built in 1770. So it's been around for a while. And if you haven't learned, the U.S. is a relatively young country. We don't have a lot of these. And then I was particularly impressed by the new church. Now, for my American colleagues, the new church here in Delft was started in 1381. Okay? This is in comparison to the old church. The old church was started in 1040. We don't have any of that in the United States. The oldest buildings we have in the United States, we have a few that are like 375, 380, 400. We have one building in the United States that's been continuously in use for 1,000 years. And it's the Taos Pueblo out in the desert southwest, the Native Americans. So where you have many, many buildings that are thousands of years old, we have one. So, perspective. In the spirit of the late Stephen Covey, I'd like to just tell you what I want you to end with today. I think we do a poor job of conveying the importance of buildings. Now you say, well, we're all kind of in the building industry. You know, this is what we do every day, but we do a poor job conveying the importance. So I'm going to give you a little snippet in that. I'm going to talk a little bit about some of these uncomfortable trends. They've asked me to really do an 8-hour workshop in 10 minutes, so hold on here. I'm going to try to give you Chris's crystal ball, where I see this is going with regard to efficiency and sustainability and resilience and circular construction. And then I'm going to ask, what is our responsibility? What's our responsibility as building professionals, as standards developers, as engineers and architects and scientists? What should we do? Who am I? I'm the luckiest guy you know. I've been fortunate enough to focus on building performance for over 35 years. It's what I went to graduate school to do. I've helped write the National Energy Code for our country. I've helped to write the state energy codes for my state. I've been an ASTM member for over 35 years, and I needed a break from building science a few years ago, so I took up beekeeping. Well, the joke was on me. Honeybees, as you know, are probably one of the most amazing building scientists on the planet. You can thank them for about 1 out of every 3 bites of food you eat. To give you an idea about the honeybee, they control the brood nest temperature, where they raise their young, to about 34 plus or minus 1 degree. Now, we have a hard time doing that with a thermostat, and they do it biologically. So, a quick audience survey. How many of you, the house that one of your parents grew up in is still standing? Okay, most everybody. Okay. How about the house that one of your 4 grandparents grew up in is still standing? Okay, we just crossed 100 years. How often do we stop and think, as Oliver challenged us with, I'm about to make a decision that's going to be with this building for 100 years. Think about what we're working on today. Cesar and Oliver both gave examples of how we do lots of innovation, but sometimes we try to do things cheap. And all too often cheap equals a shorter life, or less durability, or less long-term reliability. So, why does this matter? So I'm going to share with you some of my perspective as a building scientist on why buildings matter. I'm going to share a little U.S. Dirty laundry as well. So, first of all, this is U.S. energy consumption. Now, if you ask most people in the United States, where does our energy go? They're going to say, oh, it's transportation, it's energy, it's industry. No, most of our energy goes to buildings, about 40%. And it's roughly, the automation, the translation is messing up the numbers. Forget about the numbers aren't important. The important thing is that this building energy use is roughly equally split between commercial and residential buildings. We, as building industry professionals, are terrible at conveying the importance of what we do every day. And it's because of this. It's because of the stuff we plug in. We have an insatiable appetite for electricity. It shows no sign of abating. If I travel around the world, everybody everywhere wants that stuff. So where do we get the food to satisfy that appetite? Well, this is not a particularly interesting chart. You know, in the U.S., we've got some nuclear and renewables and various other fuel sources. This is not particularly interesting. What's particularly interesting is this one. About 80% of where we get the food to satisfy that appetite, to meet that demand, is from a finite resource. Now, we all learned in college about finite resources. Once they're gone, they're gone. Now, they may not be gone in my lifetime or in your lifetime or children's lifetime, but we've forgotten the economics of finite resources. This is one of the reasons that Cesar was talking about the resource of fly ash and where is it? And Oliver's talking about all this material substitution. You know, we're trying to use stuff smarter. If you're a green building nerd like me, you might think of buildings in terms of their carbon footprint. And in the US, we find suddenly that buildings are our biggest polluter. Or said another way, the typical US house pollutes twice as much as the typical car. Now, we don't think about that because the typical car has exhaust pipes. But the exhaust pipes for the building are out of sight, out of mind, down at the local power. We have failed to convey the importance of our buildings, whether you believe in climate change or not. Both of my predecessors spoke about water, and again, we did not plan these presentations, but over half of the extracted surface water in the United States goes to make electricity. That's about 3 times the amount of water going over Niagara Falls every minute. Now, we don't think about that. Water, buildings, energy. Well, coal and nuclear plants require cooling towers, and we put all of these power plants on rivers and lakes that have access to water. In my home state of North Carolina, 85% of our extracted surface water is used for coal and nuclear cooling. So we might think about, you know, how do we influence the minds of people? And noted social scientist Abraham Maslow defined the hierarchy of need. And we notice that, you know, here at the base of this pyramid, before we can get up here to self-actualization and self-esteem, we have to first have food, water, shelter. That's the business we're in. It's the fundamental. Now, we now know that Maslow was wrong. We have to first have Wi-Fi, but beyond that, we've got to have food, water, and shelter. And everybody wants to be green. I do a series of workshops on sustainability, and one of the things that makes the attendees of those workshops uncomfortable is green is very personal. If I'm in the desert Southwest in the United States, I've been fighting over water for hundreds of years. Well, we're having water shortages in the southeastern part of the United States where I live right now. And so if I'm talking about green building in Atlanta, Georgia, for example, I have to talk about water. The parallel I like to draw is, I go into the grocery store to buy cereal, a box of cereal. I have high cholesterol, so I'm looking at triglyceride content, fats. Person next to me has diabetes. They're looking at the same box of cereal, but they're looking at sugar content. Person on the other side of me has high blood pressure. And they're looking at the same box of cereal, but they're looking at salt content. We all three have the same objective, sustainability, but we value different things. If you're below sea level, you're going to be valuing safety and evacuation and recovery post a disaster event. And so this question of being green requires uncomfortable things that we can measure. And this is one of the things that comes up. We rarely ask this tough question here: for how long? You are blessed with marvelous buildings of antiquity and infrastructure that's still performing today. Why? Well, because it was very energy intensive on the front end. Think about glass. How do we make glass? We melt sand. It's very energy intensive. What do we do at the end of this glass's useful life? We make more glass. Right? So if I want to be green, and everybody talks about the road to green, some people will hammer energy efficiency because that's their passion and what they care about. Some will focus on water consumption. There's certain things in Maslow's hierarchy of needs that are not optional. Water you can drink, air you can breathe, not optional. Durability, resilience, finite resources. I'll show you some of the implications of that. Again, we didn't coordinate these presentations, but in the United States, over 40% of what goes into our landfills is construction debris. If I share this slide with a third world country, they would look at our landfills as a supply chain. And that's what we're learning right now, is that I predict in a few years that the people that own the landfills are going to be, some of the biggest industries in America, because what do they have? They have the stuff that we used to throw away wastefully. They have the metals, they have the plastics, they have the coal combustion byproducts, all of that stuff, which today we now think of as raw materials in a supply chain. Some other examples: asphalt roofing. What do we do when we rip off a roof? It used to go in the landfill. Now we're looking at construction composites and blocks and civil engineering usage and ways to have acoustical attenuation with asphaltic products. Glass bottles, they used to just be thrown into the landfill, but now they're the primary feedstock for fiberglass insulation and the next glass bottle. So materials repurposing is something that not just these handful of industries are looking at, but all across the compendium of ASTM committees that are thinking about buildings and building performance. So I'm going to share with you just a little perspective on Committee E6, one of the committees that I'm very closely involved in. Don't pay attention to all these words, and we'll give you a copy of these presentations. There's a lot of subcommittees. They do a lot of things: durability, air leakage, energy, safety, metal roofs. But what I want you to pay particular attention to is how many of these subcommittees have the word performance in their title. We've learned that it's not okay to build a building. We then put people. And people have to breathe and have to be safe and have to be fire safe and have to be able to evacuate in case of an emergency, and have to be comfortable. I could build a building here in the Netherlands with single glazing. And it might last for a long time, but no one is gonna want to sit next to that window in the winter because it will be cold. No matter how much horsepower we throw at it, no matter how much tonnage or heat we throw at it. So measuring things has gotten quite sophisticated. We can measure window performance, measure wall performance, measure structural performance, measure compressive strength, do accelerated weathering, accelerated aging. We as a young country in the United States are learning a painful lesson that we need to measure more to demand more. This one is close to home for me because I live in Asheville, North Carolina, and we've just had, in 3 weeks, 2 hurricanes. And while this picture is not nearly as sobering as what we saw with Katrina, if I were to go out to the coast of North Carolina and tell you that we had areas of our coast that received 1 meter of water in a day, in a place that had never experienced that before. So, did the infrastructure hold up? What do we do to recover afterwards? How long will it be until that infrastructure can serve the people who are going back home and need to rebuild? Close to home here for you in the Netherlands and all of us as world citizens was the recent earthquake and tsunami in Indonesia. And then, just last year down in Texas, near where Cesar went to school, Hurricane Harvey. We're not used to this. And while all the climate scientists say that the extremes are going to be more extreme, no matter how many deniers we have, the data, those of us who are driven by data, see exactly the data trends that have been anticipated. The good news is we have the ability to change. Now I will say, change makes everybody uncomfortable. I can explain to builders why they maybe should change a wall construction system that we learned 200 years ago would be a better construction system. And I can show them how they could use less material, it'd be stronger, better insulated, more durable, less waste. But I ask them to do the one thing that makes us all uncomfortable. I ask them to change. The good news is we have tools today that will enable making change less painful. We used to wonder about the air leakage of a building. Put on your mechanical engineering hat for a second and let's size the equipment for this building. We know the wall performance, we know the window performance, we know how many people are in here, we know the lights, the copiers, the computers, and the elevators, but what's the one thing we don't know? We don't know the building's air leakage. We now have the ability to test the air leakage. What if we were to test the air leakage before we size the equipment? Oh, we would just reduce the error bars in every mechanical engineering calculation for every building, reduce the equipment size, it would perform better, longer, and provide more. And we can do this for really big buildings. This is really difficult technology. It's called a fan and a pressure gauge, and we can measure the air leakage. Committee E6 focuses on a lot of these building performance issues. Air leakage through windows, curtain walls, and doors. Structural performance of windows and doors and skylights. Forced entry resistance. Installation of windows, doors, and skylights. I can build a perfectly good wall and I cut a hole in it. How do I put the window in there? How do I manage the water in such a way that it is consistent with the water drainage system of the wall and the roof? The other thing that is really interesting in E6 is that we provide standards to help those that are trying to help make buildings better. For example, standard guide for evaluating exterior building wall materials, products, and systems. What does a commissioning agent who's helping to bring a building up from the ground, what do they have to look for and look at? And what do they have to record? And what does the building official need? We have standards. How do we evaluate water leakage? You know, a lot of buildings that we're doing now, we do a water leakage test on site. Why? Because it's easy and we learn when we measure stuff. We start asking questions like, how did it fail? How serious is the failure? Is this going to compromise the structural integrity of the system? And then what do we need to do? What do we need to measure? What can we salvage and reuse? I could spend all of my time on this one slide. I'm just going to share with you one example of standards as a critical element of education and market transformation. I'm going to talk about windows. I spent a lot of time in my life thinking and working with the window industry. The window industry has a hard job. How do I know the energy performance of that window? Well, until a few years ago, we could look at whether it had one pane of glass or two. We could visually inspect that. But does it have low-E coatings? I don't know. They're invisible. How about argon gas fill or other gas fills to suppress convection? No, it's invisible. So the window industry had a lot of innovation, but their job was difficult because they're selling the invisible. So there was a need identified. We need to understand the energy performance of windows. And so if we want to get to market transformation, we had to have the research and product development, and we developed test methods and simulation methods and a rating system. And rating systems require what? Measured stuff. We had the data from the test methods. And then once we have the data, we can do third-party certification and put a label on the window, and now every window in America has a label on it that gives its U factor and solar heating coefficient. But that's not market transformation. That's just the opportunity for market transformation. You have to then get the industry to engage in it. And that's why the window industry and the glass industry and the building code industry all worked in this regulatory arena to get broad adoption and then get it into the building code, get it accepted into the marketplace, and to transform the market. Now, this is not a fast process. Why? It's not that we could just write a law. We had to first have the industry involvement and participation. That's what happens in all of these ASTM committees, just like here. The industry rolls up their shirt sleeves and works to solving a problem. We had not only the window manufacturers here, but we had the laboratories here. We had the government regulators here saying, here's what our building official. Put yourself in the shoes of a building official for a second. You walk up to a window. What's the energy performance of that window? Does it meet the code? And now we have that market transformation. The trouble here is that market transformation takes time. The building industry, even though it's very innovative, as my predecessors have talked about this morning, even though it's very innovative, it's very slow to change. Because why? Because change makes us all uncomfortable. Even change in our own best interest. I have my own building science project. This is a 150-year-old log cabin that is my personal building science project. I call it my building science project for life. I just hope I live long enough. It has 5 building materials: stone foundation, wood logs, mud chinking, a metal roof, and a glass window. 5 building materials. How many building materials do we deliver to the typical job site today? 50? 500? 5,000? Most of which are not necessarily designed to go well together. And we expect them to withstand the forces of sun and wind and rain and climate change and 3-year-olds. For how long? So, to conclude, buildings matter. I used this title just as a reminder that we could spend I do 8-hour workshops on these topics, but the point here is that we've got to do a better job of prioritizing building performance. And we've got to first plan for it. We've got to engage the building industry and the suppliers to the building industry and the regulators of the building industry and plan for it because of the interconnectedness of buildings to all of the challenges we face. We've got to not be afraid to measure stuff. We've got to measure more stuff. When we measure things, we learn. We like to throw out that word sustainability and green building. But what does that really mean? Well, for me, it means a long time. When I walk the streets of Delft and Amsterdam and the places that I visited while I'm here, I'm heartened because there's a fundamental sustainability in the longevity of your buildings and the communities that have been built here. And we don't have that in the U.S. We're a very young and often arrogant country and we think that, we have to cut costs. And I would like to pick up lots of these buildings and take them over and show them what can be done and what maybe we should do. Standards are an essential step on this road to market transformation. Like Oliver, and again, we extend the invitation. I think that if you were to ask any ASTM member and you were to share any interest on any topic, they would say, oh, you should join us committee week. Please come and participate with us. We need if you've got specific skill, knowledge, and expertise on a given topic, we've got a place for you to participate and help make buildings better. E6 meets about every 6 months. We're going to be meeting next week. We've got we're coming up on 300 different standards on the performance of buildings. And I say that we haven't touched all the topics yet. Interestingly, Committee E6 is the founding home of what is now our separate committee specifically on the topic of sustainability. So I invite you to join us. I appreciate the opportunity to be here and share with you, and thank you so much for hosting us. The future is in our hands, so thank you very much.
The next panel is we start with the first one from, let's see, yep, with Jaap Germaine, and he can introduce himself again in a minute. And then followed by our three Dutch speakers, variety of input. So we have Simon Wijte. He's our chair of the. I have to say it well. What's the number? The committee. Yeah, TGB. Concrete. So concrete. So he's our chair for on the concrete side in NEN. Furthermore, he does a lot of knowledge when it's about concrete and constructions. We have Pim Peters. He asked me to not say too much about his background, so I only say one word. I want to be unknown. That's Dutch. That's Dutch. You want to be just say my first name. It's Pim. But he was a proclaimed constructor of the year in 2017, and I say he has an amazing CV. So that's him. He will bring us forward in the idea of also on constructions. And then we have Jaap van der Heide. He's senior advisor with Rijkswaterstaat. We don't have a translation in that, I think.
No, but for our American colleagues, Rijkswaterstaat, I'll shortly mention it, but it's sort of what you get if you were to merge the Federal Highway Agency with the U.S. Army Corps of Engineers and bits of the EPA. So that's all.
And all the three of them are involved heavily in standardization on the NEN, and especially in the NEN side, the European side is the same. So, but we will start with Jack, and afterwards we do the same. So we have questions and some debate on the end of the four presentations.
Thank you, Harold. Good afternoon, everybody. you cannot join an ASTM committee, okay? I need to know you're alive. That's the first piece of this. My name is Jaap Germaine. As everybody here, well, not everybody, but most of the ASTM people, I wear two hats. One of my hat I actually get paid for, which is I'm a research professor at Tufts University, and before that, I was a research associate at MIT in the civil engineering department. I am essentially a geotechnical engineer, and I do research on material properties of sediments, soft rocks, and things like that, and teach a variety of classes. So moving forward, so this is going to be a relatively short presentation, and I know this is completely different from what you've been talking about, because my world is the world that holds your world up for the most part. So everything we do, you don't see, but this is the sorts of things that we think about. I'd like to start the presentation just talking about the civil and environmental engineering sector. And my perspective on this is we are completely different from most of our engineering colleagues. What we do is we engineer society's world for the most part, right? We're the guys who are responsible for where people live. We're responsible for the environment, and from that, if there's waste that needs to be cleaned up or contaminants in the environment, it's the civil and environmental engineer who steps in there and takes care of that. And we're in charge of our waste stream, and that's our waste stream from the physical side, the solid waste, municipal solid waste, commercial solid waste, as well as the liquid waste, right? Going through sewage treatment plants, the infrastructure that gets it there. So a lot of what we do, people just essentially take for granted. You go into a building, you expect that building's going to be there. You don't worry about, wow, is that ceiling really designed to be okay? You drive over a bridge. You expect to get to the other side. You don't think, hey, man, whoa, I'm way up in the air here. This is a problem. So within what we do, we worry about the safety, but we're also constrained by the effectiveness. We have design constraints that we need to be cognizant of. And we are generally, if we're responsible civil and environmental engineers, we worry about the environmental impact, and we try to reduce our footprint whenever we're doing our designs. And then finally, we deal with the water supply system, where the water comes from, how it gets cleaned, treated, put into the distribution system, and so forth. So it's a wide-ranging piece of the world. There are extremely unique aspects of what we do, and these are the ones that I think are by far the most important. We generally design for extremely long periods of time. We like to think 50 years. You folks may be thinking 200 years for all I know, but we're not thinking design cycle that I build this washing machine, I want it to last for 5 years, and then I'm going to sell you another washing machine, right? Somebody buys my building, they think it's forever, right? So that's important. It means the scale of things that we do, prototyping is not possible. You can't take a CD design and change it a little bit and see how long that lasted and try something else. We build things, it's a one-off deal, and essentially we cannot prototype to see how well things work. Our replacement costs, this I find extremely important for us. Replacing civil engineering infrastructure costs probably 10 times more than the first time that we built it. It takes many more years to build the second time that it does, and it has a huge impact on society. When you want to change out a bridge, you have to figure out how your infrastructure is going to work around that bridge, and that is a huge impediment to us moving forward. We very often have to remediate things and in ways that are probably less than ideal. Next is the size of the problem we deal with. Massive amounts of materials. And in my world, you see up here, this is an arched landfill dam. That's an enormous amount of material. We're going to be green with that? We're going to recycle all that material? I don't think so. It's not going to happen. You take the concrete from a structure, if you're gonna break that structure apart to reclaim the concrete, there aren't a lot of places you can put crushed concrete. We generally create more materials in doing those things than we can consume in second use type things. And then finally, we are not in a position to accept failures. So my CD cannot, or my building can't fall down and make that an acceptable situation. I'd like to now change gears a little bit and talk about what my committee does. And my free job here is I'm the chairman of the ASTM Committee on Soil and Rock, which is D18. And we're the people who write the standards associated with how you characterize the materials, either from the characterization of the physical properties or the mechanical properties, the strength, compressibility, permeability. We do things about site investigations. We do in situ measurements, lateral deformations around buildings, quality control type things in both the laboratory testing and in the field applications. So that's where most of my time gets spent in the volunteer world. The committee itself is relatively large. We have 1,200 members. We are responsible for 365 standards. And nobody mentioned this yet, but in the ASTM world, every one of those standards has to be reapproved within 8 years. So this is a tremendous workflow that we're responsible for. I sit over 22 technical committees, 11 administrative subcommittees, and our member composition looks like this. We have 14% of our membership is from international members. We have representation from 52 countries, and actually 2 members from the Netherlands participate. And then we have some academics, government, nonprofit people. A little bit of a historical perspective, and I think there's a very nice back message to this. This committee was started in 1936, and our initial objective was essentially road construction. And at that point in the United States, there was a massive amount of infrastructure being put into the road industry, and that's why this committee was started. It was actually started with 9 standards, so we've gone from 9 to 365 with another 50 or so that are in the works. Over the years, we've expanded our scope, and we've expanded from these 11 subcommittees, which are essentially in the fundamental areas of what you would consider civil engineering. We've expanded to specialty areas. So we had a subcommittee on marine geotechnics to service the oil industry at that time, rock mechanics, frozen ground to deal with problems in Alaska and places like that with permafrost, admixtures to get us into the various things that were being done with difficult soils, to either add lime or cements or things like that to make those more usable in the tough material category. And then a cute little group here who does bulk solids, and these guys deal with cornflakes or coal ash or cement powder, and it's all about conveyance of particulate materials, which is what I consider low stress soil mechanics basically. And then we've had a variety of what I would consider major initiatives, and one is a new committee that was spawned off from our activities, which is one on geosynthetics, which deals with liners in landfills and things like that. Another one on groundwater and vadosome, which is a subcommittee that was developed because the US EPA needed some standards in a particular area, so we started an activity specifically for that. And that particular committee has now grown to the point where they have 100 standards. So they have almost a third of all of our standards out of a committee, or subcommittee, that was brought to us as a problem area. And I think that's one of the really strong points of ASTM. It's a relatively nimble organization that can change depending on what the particular objectives are. And like everybody else in ASTM, I will make a joke about the Cannabis Committee because we had to do that because We were coming here, I think, isn't that why? Anyway. And then more recently, erosion and sediment control technology, which is dealing with slope failures and that were generated by flow of materials of water on shallow slopes and so forth. So I'd like to just look at then 3 areas where I think we are green, sustainable, or maybe somewhat circular. And we have specifically the sustainability subcommittee, and those folks are worried about recycling of materials and writing standards to quantify those materials as they go into a second life. And this was a subcommittee that we formed in 2008, so it's relatively timely. And you can see here's a list of 5 of those standards. One's dealing with the reuse of scrap tires. One, the fly ash problem, foundry sand, asphalt shingles, and processed waste. So there's an example of a subcommittee that we have that was developed specifically to try to deal with how you're going to measure properties of these recyclable materials so that you can quantify what their applications are in uses. The other one I'd like to say a few words about is the Sediment Control Technology Group, which is D1825, and they write standards essentially to protect slopes and embankments and so forth against high erosion events. These folks specialize in trying to reuse materials or use natural materials that will biodegrade over time, and then I suppose that's how they will end up going back and rehabbing the slopes. So we have the live fascines, which are basically these staked walls that you put up with growing material, and the material grows in place and then becomes a live retention. Sediment retention device effectiveness, fiber mulches for planting things, wood fiber mulches, so places where you can take natural materials, put those into a situation where they essentially have a second life. And the last one I'd like to talk about is just a general soil characterization, which goes into measurements that you need to know about the chemistry of the materials, which are not specifically written for the reuse, but are certainly important if you're thinking about reusing soils in different environments. So we deal with with standards characterizing peat, water solubility of chlorides, oil sorption, and orthophilic clays or manufactured clays so that they will absorb oil or other contaminants. Measuring the pH, the solubility of salts, beryllium, and soluble sulfates. Now, I will say we don't do a lot in the soil chemistry area, and the fluid chemistry piece is basically with another one of the ASTM's committees, which is DO9, and they actually measure specifically water properties. So with that, I think I'd like to thank you. I don't want to take too much time. I will be more than happy to answer questions when we're all finished, but it's an absolute pleasure to be here and look for areas of collaboration. That's what it's all about.
So we continue. So for sure, I think from the 4 presentations we saw the importance of standardization. And I would almost say if we saw all these work in those STM committees, you can almost copy that to ISO to CEN. We have comparable number of standards within ISO and CEN. So I asked the Dutch speakers not to go into detail on the standards, but more a holistic view, a general view on sustainable constructions. So they give more a little bit different presentation, but I think it will be interesting for the discussion here. I think the best is to start with Professor Simon.
Yes. He made his own choice there.
Which I may not say professor, but now I do it. Let's see. Simon. Yes. So just go up and down, Simon.
Okay, thank you. Thank you that I may try to explain you something about circular use of concrete structures and concrete structural elements. I'm a part-time professor at Eindhoven University of Technology. Over there we have two professors of concrete structures, one on the new, my colleague Theo Salet, who's working on 3D concrete printing, and I'm looking after the old. And my chair is called Sustainment of Concrete Structures. When I start my lecture about sustainment of concrete structures, I start with a picture of this building, and I ask my students, do you know what material it is? Well, they're rather smart, and they know I talk about concrete, so they guess, well, that will be concrete. And indeed it is. It's a building constructed, let's say 100 years after birth of Christ. And the Romans they were familiar with concrete already. And the concrete they created in the Pantheon has a compressive strength of 20 MPa. I've converted that for our American guests. It's around about 3,000 psi, which is not so bad. And to my knowledge, the building still has the biggest span of an unreinforced concrete structure with a little bit over 43 meters, a little bit over 120 feet. That structure is still very capable of resisting the forces that are acting on it. And from that, it is without discussion that concrete structures which are used in a mild environment are durable for a very long time. And in that, it is different from a lot of other parts of the buildings we have. Stuart Brand describes it in his concept of the 6 shearing layers of chains, where he divides a building in 6 parts. Well, we have the stuff that's there for a month or a day. Space plan, well, I don't know. My wife wants to change every now and then, so it's there for 3 to 30 years. Services, so electrical, mechanical, 7 to 15 years. The skin, 20 years. Well, maybe let's make it 50. Then we have new installation requirements. The structure will be there for 300 years, easily. And I can say that for concrete, but that is also the case for steel or timber whatsoever. And the site, that's our problem, that's infinite. That's what we have to do with. So the structure is there much longer than all the other stuff that creates the building. That, with respect to concrete, when it's used in a mild environment. How many concrete do we use in a friendly environment? So we look after the concrete placed by the mix suppliers, ready-mix suppliers, and from that we learned that more than 50% of the concrete they were creating is based and is created to resist environmental classes which are mild, just dry or very moderate wet, so no problem. So most of the structures are very well in durability. So here I made a statement that when a concrete structure is not durable, it never can be sustainable. What to do with those structures? And in the campus of our university, we have a very nice example, or indeed we have 3 very nice examples. Our university is not so old, it started after the Second World War. Eindhoven is the location where, for the American friends, Philips is based, was based. Our campus was built at the end of the 50s, and there are 3 main big buildings in that style, concrete structures, curtain facades, and well, as you can calculate, those buildings are now 50 or 60 years old. The facade, out of date, mechanical, out of date, electrical, out of date. The structure is still there. So what did we do at the university? Those 3 buildings were replaced. We circular used this concrete structure. So the house of our department, the built environment, used to be the building for chemical technology. It was completely stripped, so here you see a picture of that. A recess was made in the structure, a new facade, so we have a complete new building. Electrical department, stripped layer by layer. And every layer there was a new place, and now it's a student housing. So we have here a very beautiful picture of a concrete structure when it was fully fixed and stripped. We replaced the facade. We brought in, for instance, precast bathrooms to speed up the construction time. So within the period of 1 year, the complete building was
redone. Everything was new, except for the circular use of the concrete structure. And this was our main building. In the future it will be called Atlas. There the construction order was quite different. They first stripped the building until the asbestos. I don't know the English word for that. Sorry. Asbestos. Then they took the asbestos out, and then they started to build it up completely. It took them 4 years. But now, when I look out of my window, it looks like this, and it's almost ready for use. But the building was already designed also, and then I come to another sort of point. This was designed to reuse the structure. The structure within the building is very flexible. We had alternating concrete and light steel floors, and even the concrete floors were built in a way with in situ concrete, precast concrete, that recesses in the floor could easily be made. So this structure is very flexible. And I think that is something that we have to learn, for instance, to our architectural students, but also to our students in structural engineering. When you design a building, a new building now, and I know that it will be very hard to look into the future and how the demands will be 50 or 60 years from now, but keep in mind that you design a flexible building, a flexible structure, because that will make it much more easier to recycle, to reuse the concrete structure as it is. It's obvious that cannot be done with every structure. Every now and then a structure is in the way, or there is deterioration, or whatsoever. We want to make a higher building in that particular case. So what we do then is, okay, we demolish the structure, we crunch the concrete into circular aggregates, but from my point of view, that is not recycling, that's downgrading or downcycling the material. Why not saw, for instance, the concrete plates which are in those structures from the structure and starts to try to reuse them. So a master student of mine, Eline Dolkema, did perform a master study after this possibility with respect from structural engineering point of view. From an economical point of view, it will be completely different. But what we have in the Netherlands, we have quite a stock of buildings consisting of concrete frames with concrete walls with very little amount of reinforcement or even non-reinforcement, and continuous concrete slabs. And instead of completely demolish those structures, we can take existing plates from it, from the floors, and even so from the walls, and they can be reused. And for instance, they can be reused for the structure of terrace houses like these. And within our studies, he looked after several structural details, and taking the starting point that disassembly of the structure should be possible for further recycled use, as it took care of the vertical load transfer, the function of the floor, but also the diaphragm function of the floors, which are quite important. Her study did not focus on economic aspects, it only focused on structural aspects. However, when you think over the model, it is likely that there will be a party that will buy floor plates from a structure to be demolished. And that's the same party from whom you can buy floor plates to use, old floor plates to use in your new structure. That only can work. And the following statement is also valid when you want to completely reuse an existing structure. It only can work well when the actual information of those structures and those structural elements is available. If you have to determine them again, and you have to perform new research after the properties, it will never work from an economical point of view. But when you are able to keep the relevant information connected to the structure, and in that process sketched over there, so from the demolition to the stock and its new use, and you can keep the information connected to the element, then it can work. And from my point of view, there is a task for standard organization to describe how that can be done. I thank you for your attention.
So how that can be done, I think that's small bridge to the material passport, and I'm not sure if Pim is saying something about it, but
I will.
you will, okay. For me, thank you. One moment. Yes, there it is. Floor is yours.
Okay, well, thank you for your attention. I think Professor Simon, already introduced the topic I will explain you something about. And I started in 2009 with the research of sustainable construction, because it was for me a very interesting theme. A lot of structural engineers like to go in the height with high-rise, but for me the sustainability was interesting. And I started also with the implication of a donor skeleton. And a donor skeleton already says something about circularity. And I think everybody knows the outline of circular economics, the circular economics of the Ellen MacArthur Foundation. And if I transfer this to my daily work, and I'm a structural engineer, so I'm 99% busy with designing structures of building, with calculating structures of building, and with discussing with the contractor structures of buildings. And partly the last thing, the discussion with the constructor, is a main part of our daily work. And so if you want to change this way of building and the building construction industry, it really has to take a lot of effort of the designers and of the standardizations. But if I look to my profession and I keep it easy and as simple as possible, I say if you talk about circularity, you can use it in three ways for the structural engineer. First, you can design for reuse. So the main goal of a structural engineer should be, I make a structure, and the structure I can reuse in 20 years, in 100 years, and perhaps even longer, such as Simon already said. If you know that the structure will stand there only for 10, 12, 15 years, then you can reconsider or consider even design for this assembly or industrial flexible EFD design. I think the most of them know it, but this is where you reuse the structural elements because you design it that way that you can take it apart and rebuild it. And I think the lowest way of circular economy is to design it with recycled materials. So you already hear upcycle, downcycle. For me, to recycle is very good, and we have to do it, but the higher ground is in these two parts, and there we can gain a lot of effort. And in practice, I have learned the last 6-7 years, when there was a little bit of crisis in Holland, a lot of building of offices were empty. This is such an office, it's standing in Utrecht. It was an office building, and because the people that went there after 10 years, they move out and they leave the building after, and what can you do with it? Well, this ugly duck you can transform in a very nice dwelling project. And researching these structures and researching these buildings, we learned a lot. Here you see concrete facade, and if you take out the concrete facade, you get this stripped building, you get the skeleton of the building, and it's a very, such as before said, a very flexible structure. So you can, because you don't have load-bearing walls, you don't have a load-bearing facade, you get a really nice building that you can use. But I think one very important part is what's happening in the ground. So Jack already told us it's important. In Holland it's even also important. We don't use organical soil, but we use piles in the ground. Once you're going to transformate a building, the first thing you have to research is how is the foundation in the building. Because what we learned was that there was a lot of overcapacity in the building. And this overcapacity we used to place 3 more stories on the building without changing the foundation. And this is very interesting. Another thing that was already said, and what I suggest that I say something about it by Harold, and which I'm not really sure about Professor Simon, is from this building we didn't have any drawings of the reinforcement, we didn't have anything of the concrete, we didn't have nothing. The only thing we had was that we knew that it was an office and that there were, well, office live loads calculated on this structure. But if you think about it mechanically, you can research the elements that are really necessary for the structural load-bearing case. So what we said is we're going to investigate some elements, and with this investigation about checking the concrete, checking the steel and reinforcement, the costs were not very high, and with this information we could recalculate these elements, and we could say, okay, there's overcapacity in the building, there's the materials are still good, so we can reuse this structure and even top it up with some new stories. If you find after 10 places that it's a bad, somewhere it's bad concrete or somewhere the reinforcement is not good, then you have to check the whole building, and once you start to check the whole building, then the economically part will be difficult. So I think to make it happen, you have to do it steeksproefsgewijs. I think you know what I mean. I hope you know what I mean. And if somebody can translate, please. But this was for us very interesting, because when we started this and when we started to transform these buildings, I thought, well, what is the environmental impact of this decision? Why can't we better tear down the whole building and start again? So, according to, well, it's the university here in Delft, and it started in 2016 with the, in 2016 I did a research, a thesis, for to calculate the environmental cost indicator for a building, an office building in The Hague, and we checked, well, what happens if we bring in 2 stories, 4 stories, or 8 stories? Simple. Random. Thank you. Thank you very much. So what we checked was that the economically costs, if you have to reconsider the foundation in Holland, is very expensive, because if you have a cellar, you have a water problem, and the costs are very high. So scenario 3 was the scenario that we had to recalculate and re-strengthen the foundation, re-strengthen all the building. So economically it was not interesting. The most economically part was scenario 2, which we could top 4 buildings. The reason why that was because the cellar that was underneath was on good sand soil, so we could place in more loads on this foundation without any problems. But the main goal was that we also checked what happened if we build this new, or what happened if we transform. And you see that the environmental cost indicator of the vertical extension is almost 70% reduction of the environmental cost if you build it new. So it's a very big saving on the environmental cost, and therefore I think that the standard should be that we must think about the designs that we make now to be reused, and in this way it's not only to be reused multifunctional, but also think about what can we do in the foundation already that our children or children can build up more stories. If, for example, in my village Pijnacker, everybody wants to go to Pijnacker to live there, then we can build up and top up all these buildings. So I think this is something that we have to bring in as a standard, as a regulation. However, I don't know in which STME committee I have to apply to be able to bring this in. So perhaps if somebody knows, I would like to enhance. But what happens if you have a structure that you cannot reuse, so that the function cannot be used anymore? In Amsterdam, you're staying there, you're walking around in het Rokin, and there's a big new Hudson Bay, famous view. Before the Hudson Bay, it was a bank, office bank, Fortis, and after 26 years, they sold it. They were very happy that they sold it. But the one that bought it, and you see through the building, you see a lot of closed elements, wanted to make a shopping mall out of it. And in this structure, it was not possible. So what they did was they demolished all the building and they crushed it and perhaps it's somewhere under the road. Or if we are lucky, it's recycled. But what I thought, well, can you not use this, such as Simon said, can we not, instead of demolish it, take it apart and reuse these elements, the structural elements, for a second time, for a new life? This idea I already had in years before. So also in 2013 we did research about the donor skeleton. So a student went to Amsterdam in an area, Amsterdam here, and checked there all the buildings. And from all the buildings he took about 10 buildings and he take all the drawings from the archives, and he already invented or investigated what elements he had, choose 3 buildings, and from these 3 buildings he went to make a new apartment dwelling project. He calculated that. The problem that he had was that he could find from some buildings, such as in Utrecht, the structural designs, but a lot of buildings we don't have this document. So if we're starting about material passport, we don't need only a material passport. We also need a passport or like a box in where we keep all the documents that we use these documents for the next generation. His statement and his calculation was that he did also the dwelling house, the new dwelling, the project with our apartments, totally new structure and a structure with reused elements, and calculated the environmental cost indicator and came also to a reduction of 75%. So I think economically it will not be cheaper to reuse elements, and this will be the fight that we have to keep fighting. But in reduction of environmental cost, in CO2 reduction, in all this environmental impact of the construction area, we can gain a lot. Can you use it, and what do you come into? What happens? Well, in a project in Rotterdam, there were 3 buildings. The owner wanted to make 1 building out of it, but the facade was pre-war, so we had to keep the facade, and we started to take out all the inside of the building and bring in another building, bring in other stories with reuse of the facade. And when we started, and this is really funny, we started and the developer said, I'm going to rent it to Urban Outfitters. And I went to Urban Outfitters in San Francisco and I saw, well, what a nice structure. So I touched it and I saw it was like Disneyland. It was papier-mâché, it was fake. So I said to my contractor, to my developer, I say, well, what could be better now if we use second-hand elements in this project, because then your client don't have to make another second or a papier-mâché building afterwards. And it succeeded, but it succeeded because we took a lot of effort in finding elements, in taking the contractor with us, taking the authorities with us for the a permit. And this should be easier. But the people outside, for building it, they didn't notice any difference. Because you see here the columns were new elements and the beams were second-hand used elements. And they were lying on a plot of sloper, a demolisher, and the demolisher had it there for his pension because he said steel is going to be a lot of money worth. And when we came, his smile went bigger because he said, well, instead of 20 cents per kilo, I can get 50 cents per kilo. And I think after that he went on a holiday. But what's also very should be is part of the deal if you want to reuse structural element is that you have to design with this element. So you have to be creative. You have to do change your design. You have to convince the architect that this nut is beautiful. And some like it, but some don't. So it's really an effort to be able to use second-hand elements. In this project, we succeeded with about 30,000 kilogram of steel, donor steel, and new steel about 100,000 kilogram. And the reason was that we carefully checked which elements do not have a progressive collapse with them. And we choose all elements that if they collapse, then only a small part of the building collapses. It's not a big failure. So actually we designed for failure. But at the end, for the whole building, and because all the floors have a bigger impact on the environmental cost indicator, we succeeded to have a reduction of 10%. So even with a donor skeleton, and due to the fact that it's a small part of the building, sometimes you don't have a very big impact. So you really have to take care of the impact. Concrete is also possible. I thought there are research and there are some experiments. This is a very nice one. I was not participating with it, but I really liked it. That's a flat building was taken out of each other, and the upper floors were cut, taken out, and reused for a pavilion. The problem that we have now, and that's really a problem, that the regulations say we have houses that must be 260, and these houses are 240. So perhaps if you want to reuse second-hand structures, you have to adjust some standards. Or sell this to people that are smaller than us. So bring it to Spain or somewhere else. Okay, I'm really like that even the government is challenging now the construction, because in their grondstoffenakkoord, okay,
agreement on resources.
Agreement of resourcement. They challenge us with construction should use demolition waste in new construction projects. So they challenge us by using the waste for new projects. The only problem is, and in my free time I had the tendency to drink a lot, so I say, well, in my free time I'm going to apply one NEN standard document, and that's the one for reuse of structural elements. But I think to apply and to use structural elements, reuse structural elements, we need good standards to convince ourselves and the government that we can use them. Okay, thank you. Yeah.
Thank you very much.
So Jaap is going to do an oral one.
Yes, so I did a little bit different.
A little bit different.
I made some notes.
May I say from a perspective of observation?
Yes.
Yes. So
And
Jaap
I'm
van der
quite
Heide.
happy that I did that, otherwise about half of my story would have been told earlier. So I've taken some notes and I'll react in it to some of the presentations before. First, let me introduce the organization that I'm working for. I'm at Raadgevende, which is the operational part of the Ministry of Infrastructure and Water Management, as it's called, since about a year. We are an organization, I just looked it up, which was founded in the year 1798, which for Americans is perhaps quite old. In Holland it's not. I live in the city of Leiden and we have het Hoogheemraadschap van Rijnland there, which is a water board. And they don't exactly know when it was founded, but it was somewhere in between 1248 and 1255. So that has been running for 800 years. Rijkswaterstaat runs 3 major networks. That is the main road system, the main waterway system, and then the main water system. The main road system for us is basically the motorways. So we operate about 4,500 kilometers of road, 3,000 kilometers of that are motorways, and the rest of it mostly is access roads. All the other roads are operated by the provinces and by the towns. In this network we have about 2,750 viaducts, including 13 aqueducts, 22 tunnels and 743 bridges. To put it in perspective, the land area for the Americans, the land area of the Netherlands is about the same size as the state of Maryland, but slightly more inhabitants. On top of the road system, we have about a little over 2,000 kilometers of waterways, and then about 5,500 kilometers of waterways out on open water, so on the North Sea and on the IJsselmeer. 84 locks, an additional 278 bridges, which in total makes about 500 bridges, of which a significant part are movable bridges. That's basically what I do. So I think a bit different from most of the people present today. I'm a mechanical engineer. I know there's a second one. I heard about it. I did also some training in chemistry, and that's why it's perfectly logical that I'm involved in civil engineering now, I think. In the last presentation, there was a bit about the policy of the ministry that I work for, and there are 2 major objectives that have been stated by the Dutch government, and that is, and by Rijkswaterstaat following up on that, and that is by the year 2030 we want to be working circular. Nobody knows what it means, but that's the first step. And then in 2050, the entire Dutch government wants to have a circular economy instated, which means there will be no waste. Well, there comes the practical engineering mind. And when I look at the pyramids in Egypt, they deteriorate. Every single building, even the ones that are still standing after 2,000 years, they're not in the same condition they were back then. And like all of this, when you take enough time, it will return to dust. So completely circular, all cannot mean anything else, that eventually we have to reuse the dust. My phone locked. That's in easy. Then something, and that is about the durability. I heard of a bit of mixing up between sustainability and durability. Yes, we design for 100 years, but that's the design lifespan. At Rijkswaterstaat, we have seen that a bit dependent on where in the country we are talking about, the functional lifespan of bridges, viaducts and so forth will be ranging from about 25 to 30 years in what we call the Randstad, which is basically the western part of the Holland, which is all urbanized, to about 100 years in the outskirts, what we call the outskirts of our country, which is never more than 2 hours drive away. But another part of durability, when you make the connection to circular use, the asphalt roof shingles were mentioned. Well, that is something to think about. because there's something else happening. We use a lot of road bitumen in the asphalt pavements. But the oil companies are becoming more and more reluctant to sell that to us. And why is that? Because for a long, long time, it was great. They took out all of the valuable stuff from crude, and what was left over you can always sell to a construction company that made asphalt concrete out of it. Except that now they have the means to crack that stuff and make far more valuable stuff out of it than road bitumen, which has already led to the situation that in Holland there's barely no road bitumen being produced. That's something for the future. So then we thought, well, let's reuse roofing shingles, but then durability comes back into the picture, because one of the problems when you use these adjusted bitumen that is used in roof shingles, you don't actually know what you put into the asphalt. We have had new concrete pavement, of new asphalt concrete pavement, with a service life of 3 months, and that was not enough. And then we go to the reuse of structural elements, and that I think there is a distinct difference there between buildings and bridges and viaducts, and that is I discussed it just before the meeting with one of my former colleagues, and one of the main things that we want to know about the structural elements in how far is this element in the initiation phase of fatigue. But because much unlike a building, all the stuff that Rijkswaterstaat takes care of fails mostly because of fatigue. There's some corrosion coming into the equation, but mostly it's fatigue that's causing the problems. And there is one of the major needed developments that we don't have any clue as far as I know, and that is how to measure how far a structural load-bearing element in the initiation phase of fatigue. We have some first ideas which we are looking into together with Delft Technical University, but at the moment there's nothing feasible to be used in practice. The other one is the material passport, because it's something that very much which I like a lot, and that is we have had a discussion with a working group that's working on the first ideas to do something with the reuse of structural elements, and then there comes the daily practice, and that is in Rijkswaterstaat. We have seen that, and I've seen it all over Europe. I don't know how it is in the United States, but Rijkswaterstaat does less and less of the construction work itself. And that, for some reason, has led to the situation over the last 20 years that a lot of the construction dossiers, drawings, calculations have been tossed away, or at least have been stored in a location where we can no longer find it. And that leads to a sort of a disconnect, and that is that where the value of the construction itself is slowly diminishing or decreasing over time, the value of the calculation that you would typically need for adaptability is going up. And one of my other colleagues is wherever he can, he is advocating the stance that the calculations and the drawings are assets too. They need asset management too, and as lead as much as the construction itself, and perhaps even more. And that was it.
Thank you, Jan.
So, I think this gave a good impression. So after the break, it was more on the Dutch view. The Dutch view, maybe it became a little bit clearer. Is very much also driven by all the societal and governmental push on our circular economy 2030, 2050.
And that is on the pre-standardization also the role. I call it pre-standardization because we not have a fully circular market, but if you envisage that to 2030, 2050, we have to start now. Pre-standardization pilots. So mainly that's what's happening. Hundreds of people are working now on in several platforms on material passports, on terminology, or what is circular, what to do with the dust, what is, but also measurement. So I think that's so these kind of things. That's what we're discussing now. And that's also where I think ASTM or other regions come in, because this is a global challenge where we need measurement, where we need terminology and different emissions on all materials and on all buildings.